Thank you, everybody, for coming to the talk. Today, I'm very happy to introduce Sam Burden. And Sam is new faculty. Well, he has been at a new faculty since about a year. This is the beginning of his second year in the electrical engineering department at University of Washington. He finished his bachelor's at UW in 2008 and was PhD. He did his PhD at UC Berkeley, and he was a postdoc there. Sam is very interested in principles, discovering and formalizing principles of sensory motor control, neurocontrol, flight, and he's also really interested in human-computer and robot interaction principles as well. We are happy that he has taken some time to come out and talk to us.
Okay, cool. Thanks very much, Day, and thanks everybody for your attendance this morning. I'm really excited to talk to you today about kind of two big pieces of my research program that on the face of it seem somewhat disjoint, but they're kind of unified under this theme of telelocomotion, which I'll describe in a bit more detail as we go forward. Since we got a pretty compact group here, feel free to interject at any time with questions. We could try to keep this a little bit more informal, but obviously classes just started this week. I'm kind of in lecture mode again, and so I'm perfectly happy to just talk nonstop at you with no interruptions as well. So leave it totally up to you. So the leaping off point for this talk is the observation that the way that people are interacting with the physical world increasingly has elements of autonomy kind of mediating between the person and the physical world. So we have robots that are assisting in surgery and significantly improving surgical outcomes in certain types of interventions. Certainly, people in manufacturing contexts have been interacting with machines of varying levels of intelligence for a long time. Cars are now able to drive themselves in traffic. I'm not completely 100% confident that I want to be driving with them yet, but it's like kind of inevitable at this point. I think people are agreeing, and they've been helping out in aerospace fields for a long time. Then there are these like emerging applications where the machines are actually able to augment or enhance, either mitigate disability. So through this picture, a brain-computer interface is helping Jan feed herself chocolate for the first time since her spinal cord injury in like a couple decades. And then in this image, the machines are actually, passive machines are enhancing human walking efficiency. And so it's kind of taking an existing pretty good machine and actually enhancing its ability through this interaction. And broadly, just to have kind of a catch-all, every good academic needs jargon to throw around. And so just as a catch-all term, we like to refer to these as human cyber-physical systems. So like cyber-physical systems is a concept that has been thrown around for at least a decade. It's been a big program at NSF for a while, and we're kind of trying to emphasize or re-inject the human into the loop and emphasize that in these systems. So that's sort of an abstract term, and I've given really broad set of examples here. I don't work on all of these things. I work on a narrow subset. The specific problem I'm really interested in right now is this problem of robotic teleoperation. And so here we have some human, and then we have separately one or more autonomous, semi-autonomous agents out there in the world. And the human can receive data, video feed, haptic feedback, other kinds of auxiliary information from the remote robot, and then it's going to provide motor control inputs either at various levels. It could be high-level commands, or it could be all the way down to literally trajectory tracking or something like that the human's executing. And robotic teleoperation, even in and of itself, is a rather broad field, and so I want to kind of like focus the discussion on a particular problem that I think is provocative and kind of exciting. The idea that right now when there's a natural disaster like a forest fire, which in the Pacific Northwest is kind of a big deal, or just a fire in an urban setting in a house or a building, the very first thing we do is we put more people in harm's way, right? We send in first responders, firefighters, to go in and risk their lives in order to mitigate or take care of this disaster. And I just think that conceptually it would make a whole lot more sense if we could just remove the people from that setting and send in robots or machines that would bear the immediate proximal physical risk. I think the possibility of sending in completely autonomous systems is not going to happen anytime in the near future, next 50 years or something like that. But if we could just physically remove the people and have them teleoperate a robot proxy in these kinds of situations, I think that would be very powerful and have real impact, at least on those people's lives and the lives of their families. Just to kind of emphasize this point that this is like a super challenging problem, I'm going to show the video that essentially every robotics presentation this year has in it, which is kind of the summary of the fails from the DARPA Robotics Challenge. In case you're not familiar with this, basically DARPA, as a follow-up to the Autonomous Driving Challenge, tried to make they made a humanoid robot challenge inspired by the events at the Fukushima Daiichi nuclear reactor, where the idea is that rather than sending in people, which is, it's not really possible when the radiation levels are too high, we want to just send in these teleoperated semi-autonomous humanoid robots to take care of the problems. And I'm showing the fail video, it's kind of the motivation for the talk. I don't want to completely trash this because I think there were some really impressive outcomes in this challenge. But one of the things I want to emphasize in this video is that the robots often failed on their way to get to their task, right? So it was really like locomotion over uneven terrain or just getting in and out of vehicles or things like that. That was like one of the main challenges that presented itself in the final competition. And not as much, as I'll show in the end, the problem of actually doing the manipulation, twisting the valve or opening the door once they were actually there. So I'm particularly interested in this problem of how do we get how does some combination of a human remote operator, supervisor, and the physical robot actually get to the problems of interest? Scramble over terrain in a forest fire situation or run upstairs in a burning building in an urban setting?
Question.
Yeah, please.
So I'm curious, a lot of those robots that people are working with right now are two-legged robots that look like humans, right? And two legs seems like a very unstable contraption, a very unstable thing to control, and there is a huge problem like the one you're talking about, right? How to keep it stable. So why not go with something that has more legs?
Yeah,
stability.
I absolutely agree. And so actually most of my research focuses on multi-legged and not just restricting ourselves to biped, not restricting ourselves necessarily to anthropomorphic, where there's kind of a natural or obvious one-to-one correspondence between the human motion or body and then what the robot does. I'm particularly interested in what would be the principles of telelocomoting through a robot that doesn't necessarily look anything like a person. And actually in the video, there were really one robot that wasn't obviously humanoid. It was this NASA one that's kind of like a box with a couple, it had 4 octopus-like arms kind of sticking out of it. I mean, if I'm just spitballing, my ideal, or what I would initially think to solve this forest fire fighting problem or building fire problem is something like, an octopus that has I don't know, 7 legs, just something arbitrary. One of them at the end, it has a sawzall so it can cut through walls. Another one has a vice grip so it can lift up heavy things. And maybe has some chamber that you could put the dog in or something like that to save it and carry it out of the building. So I definitely agree with that observation. So the concluding observation I want to take away from this is that these robots still lack full autonomy, and I don't really think this is realistic to have full autonomy in these kinds of scenarios in the immediate kind of proximal future. So there might be some space to work in the semi-autonomous area. The other observation, though, is that kind of more broadly in these human cyber-physical systems is that even as we get better at building autonomous robots, it's not actually going to be possible, probably, for a variety of legal, ethical, policy type concerns, just social concerns, to completely remove people from these systems. And so there might actually be, even in very long term, some value in thinking through carefully the problem of engineering a system with human in the loop. And the key observation that I want to make here is that unlike kind of classical, maybe human factors engineering or ergonomics or something like that, where or even kind of a passive interface design where the human is interacting with a system that's just kind of static, or it's just kind of it has its own dynamic process that's not responding necessarily directly to what the person's doing. Really, in the case of robot teleoperation and a lot of these HCPS, we have 2 decision-making agents. So the autonomy, the robot, is learning from, adapting to what's going on in the environment, what's happening with the person and that interaction. And so it's really like kind of a game that's being played between 2 agents that have, on the face of it, very different modes of extracting information, processing information, things like that. And so this problem of just naively or sort of blithely tossing humans into the loop in control systems can be very dangerous, and there are a variety of really well-documented examples. The 2 that I'm just highlighting here, one of them goes back to the aerospace industry. Has been dealing with this for a long time, trying to develop high-performance aircraft. They kind of quickly realized that, even though they realized early on, but this problem's continued to plague even recent designs, that if you fail to take into account the kind of neurophysiological delay that a human pilot just intrinsically has, and we can't engineer that out of them, then if you don't take that into account when you're designing the gains and the time constants and things like that of your low-level control loops, then the interaction between the person and the like low-level control systems can introduce what they call pilot-induced oscillations, and those can just lead to instabilities and crashes. And that's happened in a couple of like test aircraft kind of situations. And then another example that is maybe a little bit closer to home is this idea that as we increasingly roll out enhanced safety features in vehicles, there could be some kind of bad couplings that happen as a consequence of that. So the video that I like to show here came out shortly after Tesla did that like over-the-air or whatever software update where they just sort of uniformly and unilaterally decided to endow some subset of their deployed vehicles with the ability to drive themselves. And then people, well, ideally, or the intention was drive themselves in highway situations and kind of clear skies and things like that. And people immediately started just throwing these or just deploying this like on backcountry roads and in situations it really wasn't designed for. And so what happens here in this video, it seems, is that the car is in this self-driving mode, and there's like a curve in the road that's probably fast, a sharper curve than you would expect to see on a highway. And it's also kind of this like dappled, sunlight filtering in. And we know that Tesla doesn't rely on lasers or anything that wouldn't necessarily be confused by that. They rely on actual computer vision and just regular RGB cameras. And so as this car that it's tracking in front goes around the curve, maybe the system gets confused, or maybe it kind of confuses this oncoming car as the one that it needs to be tracking, and it tries to swerve, basically. And it seemingly, in the video, it's only the human intervention that prevents the crash, basically.
Does it actually prevent the crash? We don't see what happens after this.
Oh, sorry. Well, I carefully trimmed the video for kind of maximum, yeah. But as far as I know, he just, continues on, basically. As far as I know, it's not a crash. I hope so. I should double check that. That would be.
We know there are examples where it didn't. There are people have at least one documented person who died.
That's right. Yeah, exactly. Yeah, when I started using these examples, that hadn't happened yet. Maybe I might actually change the example. Yeah, please.
I mean that there could be like two interpretations of like semi-autonomy. Like,
Okay.
One would be the human just gives basically the goal or what it wants the system to do, and the system autonomously goes there.
Right.
And the other one would be if the system is able to detect when it needs human feedback, and the system asks for human input.
Okay.
Like, I'm thinking like you're looking more at the first case scenario. Like,
I think the way that I think about it, although please push back on this if I'm mischaracterizing, I think of the way that the two cases you described kind of as related, like more closely related than the case I'm interested in. Because in your case, it's kind of this like supervisory control thing where either the human initiates its kind of intervention into the autonomy or kind of redirecting or rerouting or whatever, or the autonomy initiates that interaction request, says, hey, I need some help, I don't know how to solve this problem. I'm interested in a kind of really motivated by this like high performance sort of firefighting scenario. I'm interested in the case where the human and autonomy are continuously closing one loop. And so the level of human involvement could go up or down. That could be a knob that we tweak. But I'm kind of interested in the cases where it's like if we left the robot to do it on its own, it would go nowhere basically. Does that make some sense?
Yeah.
Cool. But they're obviously in these different scenarios, all of these different cases become like the probable design choice and the way you'd want to build the system. Yeah. So the conclusion from these couple of kind of historical observations, one older, one more recent, is that if you just sort of naively throw humans into the loop, then you can cause more problems than you solve. Or if you sort of throw autonomy into a loop that had traditionally been closed exclusively by humans, the same kind of thing could happen. So we really need to be careful when we inject things in here. And in the context of my robot teleoperation kind of motivating set of examples, what's happening here is that we have this sensor-motor loop that's continually being closed between the human and the machines. And when we intervene, like in the case of the driving, and we try to assist, we try to keep people in the lanes or prevent them from merging into traffic when it sees another car in the way or something like that, effectively what we're doing is we're altering this feedback interaction between these two agents. And necessarily, this makes a change to the closed loop dynamics. That's kind of unavoidable. And so if we don't have the ability to predict the closed loop consequences of what our interventions are going to be, then we're not going to be able to ensure safety or stability or other kinds of desirable system engineering kind of properties. So then the point of the talk today, the technical material I want to go through, are trying to tackle this and sneak up on this telelocomotion problem, starting from the top down and the bottom up. So in the first part, I want to talk about some of the work we've been doing, trying to understand how people come up with a theory for how people control nonlinear dynamical systems or control systems, and kind of base that in some theories of motor control and psychophysics and things like that. And then on the flip side, try to better understand what kind of robots we should be building, possibly with more than just 2 legs standing upright, and their dynamics and the kind of properties that we could endow them with to make them easier for the person to control or facilitate that interaction. So to start off, I'm going to dive into this idea of how people control systems. And this was basically the content of my postdoc work. So this is a couple years ago that we started this. And what we did was we tried to take a dive into the motor control literature, because the scientists have been thinking about this for a long time, since like early 1900s at least. And there are a lot of different competing paradigms or competing theories of how this works. But one popular one that meshed really well with some of our control theory perspective is this idea that humans rely on internal models. So the key thought here is that in my head, embedded somewhere, either in actuality or just at a descriptive level, I have some predictive forward model that would basically enable me to imagine ahead of time, before actually initiating muscle recruitment and stuff like that, okay, if I'm going to apply this neural signal to my arm, how will my arm displace physically in space, and how will I observe that as an output y? And then once you kind of accept this idea that there might be this forward predictive process, then you can kind of envision that there might be encoded somewhere the ability to invert it and kind of go in the opposite direction. So if I want to reach over and grab my thermos to take a drink, then what input would I need to apply to my arm in order to achieve that? And so these internal models kind of naturally come in these 2 flavors of forward and inverse. And there's a fair amount of both theoretical but also some experimental evidence that this is a reasonable description of what's happening in people's brains when they're trying to behave. And in particular, the best predictions come when you pair them. So you imagine that not only am I predicting the consequences, but I'm using that same model in the inverse direction to generate my actions. And there's theoretical basis, there's experimental basis. And we kind of latched onto this theory of motor control, partly because of its predictive power in the science literature, but also because it has a really strong parallel. It might already sound familiar to a lot of people in the room, even if you hadn't been familiar with that scientific theory. There's really strong parallels in control theory, which is really my area, but also robotics, AI, adaptive control. There are these things called the internal model principle. Some learning algorithms kind of have this flavor. And so we really thought it was a nice interface for doing kind of a rapprochement between what the scientists know or think we know about how people behave, and then how we engineer and think about our physical systems. And there's one kind of funny observation that I don't think the scientists dwelled on a whole lot, because they were really interested in how a person controls their physical plant, and so that's kind of given in advance and fixed. And they weren't really thinking of it necessarily as like a dynamical process. They were kind of thinking of it as a static input-output map. Oh, I want my hand to be at this position, so I just apply some signal and eventually it will get to that position, and there's sort of this static map. But I'm really interested in the case where the person is going to be interacting with something that really only has a clear description as a control system, something where the input does not directly map to the output, but it has to be integrated up through a differential equation or a discrete time difference equation if you want. And the input only affects the output through an intermediate dynamical state. And so I wrote it up here in kind of second order form just to emphasize that if I'm trying to fly a quadrotor or something like that, the states would be like the positions and velocities, linear and angular velocities of that device that I'm trying to control. The inputs that I apply would be something like torques or voltages on motors or something like that. And so it's relatively straightforward to kind of conceptually extend this forward model, forward modeling paradigm to incorporate dynamics in the forward model. But then it becomes a little bit trickier to think about what the inverse process of this would be. Because I can't just take a single output at a single instant in time, y, and then determine an input u at that one time instant that would, if I were to apply the input at that time input, give me the desired output. Because I have to wind up and integrate the effect of that input as it moves through and influences the physical states of the system before it will actually give me the desired output y. So we really need to think of these things as evolving in time, and the inputs as signals and the outputs as signals, and kind of mapping between those. And so in order to try to implement and just get our hands on mathematically the structure of this inverse model, we did the kind of standard control theorist trick, which is that, OK, we say, look, let's not consider arbitrary general dynamics. Let's give ourselves some structure, and let's try to work with that. So we started with models in what's called control-affine form. But it basically, you can see that what it does is it splits up the sort of intrinsic dynamics where x just influences itself, the state feeds it back on itself, and then has as a affine kind of additive additional term the part that the input is driving. So that's our control. And then those dynamics, even in that form, are still pretty complicated, nonlinear, could be kind of arbitrary functions there. And so then we invoke a relatively standard trick where we impose this technical condition called strict relative degree. And what that enables us to do is significantly simplify, basically just change coordinates so that the dynamics are dramatically simpler than they were when they were originally given to us. And the strict relative degree thing, that is a technical condition. I'd be happy to talk about it in detail offline. Just to, if you've never seen it before, just to kind of quell any concerns about it, for instance, this condition is easily satisfied in a mechanical system. For instance, if I'm measuring like the position of my quadrotor, and then the input I'm applying is the control, is a force, or like the force or a torque or something in kind of the second derivative. And really what it says, this condition, is that the input that I'm applying, the torque or the force, winds up through a well-defined number of integrals, that's gamma, before presenting itself at the output. That's really all the condition says in plain language. And so now that I've kind of done this transformation and gotten this simpler version of my forward model, all I did was just change my perspective on the dynamics of the system, just kind of did a change of coordinates. Yeah, is there a question?
Could you give some definition of when this condition is not satisfied, maybe in non-mechanical systems?
You know, it's surprisingly hard to come up with like good intuitive examples. Like I could easily write down just algebra of like some equations that wouldn't satisfy it.
Space where it's not maybe not satisfied.
But maybe it's easier to think about in terms of just linear systems. And in linear systems, what this means is that I could basically end up with dynamics. So if I have strict relative degree gamma, then if I start with x dot equals ax plus bu and y equal cx, and so this is, this was my f of x, this was my g of x, this was the h of x, then if I satisfy the condition, I can change coordinates so that I basically get a c dot equals, there will be something here times c, but the real key thing here is that my b matrix will go to zeros and then 1 times u, and then my y will go to 1 and then zeros times the state. This is really the crucial structure. And so what this is telling you is that my input comes in one state, and then what it's going to do is kind of integrate up through all of the intermediate states and then get output at the end. So my system is really kind of a chain of integrators in the right coordinates.
So it's why is your observation?
Correct, yeah. So in a mechanical system, this would just be like a spring mass or a quadrotor moving vertically or something like that. I would be inputting a force that would go through 2 integrals before being output as a displacement, a position. If that makes sense. So there is some restrictiveness in this assumption, but this assumption is satisfied for the physical systems I'm directly, proximally interested in controlling. So then with this simpler model in my hands, it actually becomes really straightforward algebraically to just rearrange and get what the structure of the inverse model would be in this setup. And so it really amounts to just like solving the equation for y in terms of u. And what we find is that if I was presently giving the right output value, then the input that I would need to provide is just I would need to cancel out the sort of internal dynamics for the system. That's why there's a minus b there. And then I would need to superimpose on top of that the gammath derivative of whatever signal I'm trying to track. And then if I had some initial output error, I wasn't outputting exactly the desired value at the initial time, I would do that, and then I would add on a kind of feedback term. And it's pretty easy to do that with just linear feedback or a nonlinear feedback of your choosing, but that's not that important of a problem. But this is what's kind of interesting is that just by the assumption that how the operator will be controlling the system, the the ODE, the plant that we're setting up to interact with, just by assuming that the way they're going to control it is learn the forward model and then invert to apply the input that gives them the output they want, this is the input they have to apply. And so it doesn't even matter, what I think is particularly interesting is it doesn't even matter how they learn the forward model, how it's represented. Like, it doesn't matter how these computations are done. We're kind of just forced by algebra that this is the input they would have to provide if they're doing what we're saying they're doing, basically. So there's kind of no slop in the prediction from this theory. There's really one prediction that comes out if you're given a model that satisfies the properties that we start with. The other really interesting thing, I think, is that that input that gives you tracking of that output is kind of forced on you by algebra. And then it has kind of an interesting implication for what happens in the system dynamics, which is that it renders the full system state unobservable. So what happens is that there might be some degrees of freedom that are not being directly influenced by the input, and they're not directly being read out in the output. So these are what we call zero dynamics. This is just kind of a convention. That's the name. So you could think of them as being kind of task irrelevant degrees of freedom, but they're actually dynamic. They're not. We can't just completely neglect them because they are dynamically coupled with the task relevant degrees of freedom. And so this is kind of a problem from the viewpoint of implementation. If in order to invert the system's dynamics, I have to apply a particular kind of input, but applying that input renders the state unobservable, it's hard to imagine how I would actually apply that input in practice, basically. It kind of introduces this conceptual obstacle. And so then one of our observations in this conference paper that we published this year is that if we impose some nice conditions, some nice assumptions on the dynamics of the system the human's interacting with, then they don't actually need to do the impossible. They don't need to observe these unobservable states. What they can do is they can learn the forward model, and then they can run a simulation in their head, kind of a virtual copy of what they think the system is doing, and then they can just use their virtual system state in order to apply the input that gets the behavior they want. So in kind of a schematic representation, the person's interacting with this physical system. It's this remotely operated humanoid robot. They have a forward model in their head. They've come up with how to do the inverse model. And all they need to do is observe the task-relevant portion of the robot's state, which is all they really care about anyway. And then just by applying the kind of input that they would get in the simulation they're running in their head using their copy of the forward model, that will cause just dynamical properties of the system that we've interfaced with the person will cause the initial conditions to converge, so that the person doesn't need to know the full system state, and they will asymptotically sort of achieve their task. Yeah, question?
So, but what if this dynamics is, zero dynamics is chaotic?
Mm-hmm.
I mean, imagine you're trying to control something in a, I don't know, turbulent air flow.
Yep.
And then, I mean, you can't, smallest differences in your inversion.
Yep.
Will mess you up, no?
No, that's exactly right. So basically the condition that we impose in order to get rid of that problem is a stability kind of condition that will basically get rid of chaotic kind of behavior. It will get rid of unstable behavior. That's the key idea. So basically, so it's like, there might be systems that a person could control that might have those kind of chaotic sort of underpinnings. But the observation is that at least using this theory of motor control, they're not going to be able to control it that way. Yeah. And so my kind of philosophical perspective is that we should be building systems and interfacing people with systems that have properties that make it easy to predict how they're going to control them, and then make the resulting behavior, what the robot actually does, robust to things like initial conditions and things like that. Yeah, please.
So this is a more logistic question.
Yeah.
So how does the person actually use your system? Like, so this is a predict and simulate forward given the model what you have, but the person only has what's the observation space and meaning how is the person doing the computation online and how fast does that need to be? Let's say for a simple example, you're right.
Yeah, let's think
ground it in my head.
Yeah, let's think about a very specific concrete example. Make it as simple as possible. Just the person's trying to control the altitude of a quadrotor. And so they're just sitting there and they're holding on to my joystick interface and they see the height of the quadrotor. That's all they have access to. They don't know, maybe it's far enough away or whatever. They don't see its exact orientation or its distance. They don't care about any of that. So they just see the height, and then they can just apply this sort of joystick displacement. That's their interface with the system. And then that quad rotor, if you want to get an idea of what these kind of hidden or zero dynamics might be, suppose that quad rotor was like carrying a load. So there's like a package it's delivering, or it had gone and picked something up that it's bringing back or something like that. Then that slung load that's kind of swinging back and forth and perturbing the height dynamics and the behavior of the whole quad rotor, it's not directly task relevant, so it's not showing up in, mathematically, it wouldn't show up in this sort of input-output simplified model I have, but it is significant, and in order for the person to get good performance as they're flying the quad rotor around, they would need to have learned the dynamics of that payload in that process. Now, I think that this, I don't envision this theory giving predictions in like arbitrary circumstances. So if you go to like the extremes of performance, like I mentioned at the start of the talk, there can start to be these problems with like sensorimotor delay in the person, right? And I'm not taking that into account at all. And so I'm kind of envisioning sort of an intermediate regime where it's not the person's just like clicking waypoints and waiting for the robot to do it because it takes a long time and it's kind of boring. And it's not like flying a jet fighter that's like extremely, extremely high performance. But it's kind of in this intermediate range where it's like, no, I need to get that thing to go from A to B, and the person can figure out, they can make the quad rotor avoid the trees, avoid the traffic, that kind of stuff. Yeah.
Yeah.
Does that help to?
Yeah, no,
make it
that's
clear?
really helpful.
So we've been doing some preliminary studies. I had a postdoc, unfortunately. Fortunately for him, he just got hired at Spaceflight Industries. So we had been doing some preliminary studies caching this out, and that's my next step is to, we have the theory, we have some kind of cute predictions, but we want to see whether and in what regime this is relevant for humans interacting with the system.
And can the zero dynamics be probabilistic, like wind, for instance? Can wind be? Does wind fall into the notion of zero dynamics?
That's a fair question. So up to this point, I've been considering the deterministic regime. So in order to get the algebra, in order to get the predictions and things like that, that's the setup we've been considering. I don't think that it would be too tough to consider, to kind of do an analysis from the control theorist perspective. The way we would treat this is like a robustness kind of question. It's like, okay, I have the deterministic control system. I did my system design and analysis, and that's what's going to run in closed loop. Now let's ask the question: if I have a disturbance coming in and it has some frequency spectrum, some content, or something like that, how much does that disturb what the system actually does? So I think we could do that kind of analysis on top of that, but I wouldn't. If you told me here's the model for turbulent wind, here's like a stochastic differential equation or something, I wouldn't be able to directly incorporate that and analyze that.
I mean, I didn't even have specific turbulence in mind in this case, but rather cases, for instance, where you have gusty wind and, well, the person is flying a drone and they apply your model, basically project backwards, saying, well, okay, maybe to turn right, I need to do this, but then wind gust appears at the same time, and then the completely, the drone starts to drift.
Right. I think
the control that the person has input doesn't have the desired effect because of this.
Right. I think if it was really like sort of every once in a while you get a gust. I don't expect any of the gusts to be so overwhelming that they immediately cause a crash, but they just sort of get me off of my nominal, and then the person has to steer back. That's kind of naturally handled, just because we do kind of have the assumption that they're closing a feedback loop in the process. I mean, I don't think that I'm really answering your question. I think I'm just like, dancing around it a little bit. But I think there's another interesting idea, which is that like, if you have some systematic structure in the way the environment perturbs the system, that you just build that up over time, because you've got these quad rotors flying back and forth delivering packages or something like that, then you could incorporate that in the dynamical model. Like we as the control engineers could incorporate that and update the way that we analyze the system. And presumably the human operator, if they're kind of, every time they fly between these two buildings, there's always this wind that's coming through or something like that, they might incorporate that into their model.
If it's systematic.
If it's systematic, yeah. So I think we need to distinguish like random versus transient versus systematic, kind of have different non-answers for each of those cases, basically. So now that we have this, this predictive theory where we've restricted the kinds of models we allow the person, kinds of systems we allow the person to interact with, what we can do now is try to provide some guarantees when we then, we as like the automation or control engineers, try to intervene in that sensor-motor loop that I described at the beginning. And so here, I've got a bunch of algebra, but the basic idea I have is that if we see the person flying the quadrotor back and forth day after day, or hour after hour, doing some task, then because under the assumptions of the theory, the observation of what they do, so what their actual trajectory is, this y, or I'm lumping together y and its derivatives into eta, actually through our modeling paradigm allows us to directly infer what we observe is the input, and then we can also observe the output. But anyway, we know what the person's trying to do. We can see the task they're trying to accomplish. And so now what we can do is try to help them along to accomplish that. So mathematically, we can just pose this as an optimal control problem. So we can kind of alter the dynamics of like our slung load and our quadrotor, these zero dynamics, in order to make it more efficient to fly the way the person wants to fly or something like that. And then the interesting thing is that under the assumption of this modeling paradigm, that the way the person is controlling the system from the beginning was by learning the forward model and then inverting it in order to get it to go where it wants to, then we can actually guarantee that our intervention improves performance. And so in some sense, we can get a kind of a proof subject to the modeling assumptions with respect to the person that this alteration we're making to the sensory-motor loop is safe, improves performance, or some criteria like that, basically. And again, this is something that we're trying to test now experimentally to see whether, person learns to fly the virtual quadrotor, we then make an intervention. Do they really go back to doing the same thing before, so they really relearned the model and then re-inverted it? Is that really what happens? That's what we're trying to test. Cool, so that concludes what I wanted to talk about on this human side. And so now I want to shift gears and talk about something that's initially, like I said, going to seem pretty separate, but I'm going to try to bring them together at the end. I want to focus on the dynamics of the terrestrial robots, potentially terrestrial robots sometime in the future, that the person might interact with, and trying to get better properties on those dynamics to make it easier for the person to control. And so the starting off point here is the observation that there's a pretty well-established and complete theory of the dynamics of animals or robots that are moving around in fluids. So whether it's aerodynamics or hydrodynamics, we understand that pretty well, kind of from first principles. I can, in principle, write down Navier-Stokes, and that has everything in it, even though I can't solve it or do anything practical with it. Yeah. But on the terrestrial side, it's even worse because we don't even have a Navier-Stokes. We don't have a fundamental first principles pterodynamics. But there's been a lot of recent progress in this area, spurred by the idea of autonomous robots and things like that. And so we're kind of beginning to sneak up on it. But the key thing that I want you to take away is this idea that unlike flying or swimming, moving through fluids, these legged things, their interaction with the world involves this kind of like intermittent contact or intermittent interaction with terrain or objects, things like that. And so then mathematically, in order to model these things, it makes some sense to think about, at least at kind of a first level of abstraction, to think about the different contact modes that our agent might have with the world. So I'm showing some pretty cool early high-speed video images from this Muybridge person. This cat, as it's running along, it has different subsets of its legs in contact with the ground. And at least at a first-order modeling approximation, the dynamics really depend on which subset of the legs are in contact with the ground, because basically every different subset determines a different number of constraints that the system has to satisfy, and at the very least, when my leg's on the ground, it exerts a very different kind of force profile than on the body than when it's in the air. And so at a coarse or parsimonious level of modeling, I want to incorporate that into my dynamical model. So I end up with second-order systems that have kind of contact constraint forces being introduced, and then there might be even an abrupt or sort of discontinuous transition in the system's velocities when limbs strike the ground. So when I'm running and my foot hits the ground, it's like very quickly it goes from some velocity to then like zero velocity stuck on the ground. So the kind of first pass at making an abstract model of these things that I might come up with are going to have this piecewise defined flavor where I'm switching between different contact modes. And there's another observation, which is that when you move away from humanoid biped, where it's kind of like, okay, if I'm walking across this room, it's like I put my right foot, then my left foot, and then my right foot. If I look at the way that successful multi-legged locomotors move around, they often have their legs hitting the ground at almost the same time. So if I'm thinking of a gait that I want to use to traverse a rocky, rough terrain or something like that to fight a forest fire, I might want to draw some inspiration from what animals are doing here and kind of leave the exact footfall sequence up to interaction with the environment. And in fact, so a lot of, basically as a consequence of the fact that a lot of animals do this, a lot of the robots we build have this same property where multiple of their legs are hitting ground at the same time. But what's interesting is that if you kind of combine these two observations, that the natural models for these systems seem to have this piecewise character, and then the natural behaviors, or the behaviors that we observe in a lot of these systems, have multiple legs hitting the ground almost the same time, then you immediately arrive at some kinds of inconsistencies, at least for a lot of the robots that we try to build, or like the simple models that we try to make for them. And so there's this kind of pathological thing that happens when you build your robot out of a collection of rigid bodies, which is that, and there's kind of been a sequence of papers published on this, some in manipulation and then some in locomotion, but the intuition here is the following. If I try to make a rigid model of my hand, so it's like every one of my segments of my finger is a rigid body, and then they're connected with rigid links. And then I try to imagine what happens when I grasp my water bottle. That model mathematically has a really bizarre pathological property, which is that suppose I have some subset of my digits already in contact, and then a final one is coming into contact. If it impacts with non-zero velocity, any non-zero velocity, then in order to satisfy all of the constraints in the system, some subset of the fingers that are initially attached have to pop off. And what's even weirder and more annoying, which kind of doesn't happen when I tap my finger on the bottle, but what's even weirder and more annoying mathematically is that the subset that have to pop off isn't determined from first principles. You actually have to make an additional phenomenological assumption. So you basically have to choose your impact model, and you have to either trust Poincaré or Newton or Leibniz, or there's like a dozen different of these mathematicians that came up with different possibilities. So to my mind, what this is telling us, this is not a property of the physical world, at least the physical world that I work in, where I can tap my finger on the mouse all day and I'm not going to cause problems. This is really a problem with our modeling paradigm. And so it might be the case that if we just kind of change the paradigm or change the systems that we apply it to, we might get much better results. And so that was kind of my philosophy coming into this problem. And the basic observation we made is that really it was the combination of rigidity with intermittent contact or impact that was causing these pathologies to show up. And if we just relax this assumption of rigidity, which in reality is just a mathematical abstraction, there are no rigid bodies really fundamentally, and especially biological bodies tend to be very compliant, then this problem completely goes away. So mathematically what happens is that if my limbs are kind of rigidly inertially coupled, that's on the left side of the picture, then whenever there's like a simultaneous contact kind of thing, you can mathematically get several distinct outcomes depending on exactly what the order of impact was or which subset of limbs you decide to pop off. But if things are squishy, compliant, if things are not rigidly coupled to one another, then you just get a unique answer and you don't have any of these problems, basically. And so we have some results on kind of what the properties of these kinds of systems are when you relax this rigidity assumption. So that, qualitatively, this is the kind of behavior that we sort of expect to get. And there's some interesting kind of side benefits that we get by removing this rigid coupling assumption. One thing is that we can exploit some kind of passive stabilization effects that arise due to this softness or this kind of viscoelasticity in the legs. And so we have some results on kind of passive stabilization of rotation degrees of freedom when multiple things are touching down. So that's kind of convenient. So you would get exactly the opposite. You would get extreme sensitivity to initial conditions and divergence of trajectories if you did things rigidly, but if you kind of soften them, then that goes away. Another thing that you can exploit is, I end up with a lot of degrees of freedom when I'm thinking of a multi-legged beast, multi-legged robot, but by exploiting this kind of decoupledness in the legs and designing the control law carefully, you can actually dramatically reduce degrees of freedom. We have some results on that as well. So kind of controlling to leverage these impacts in order to simplify the dynamics of the system that you need to control, lower its effective dimensionality. And so another kind of main upshot and future work that I'm pursuing with my students right now is to try to take this new modeling paradigm where we've sort of softened things and we just change the kinds of robots we allow ourselves to focus on and we try to control. And then what we want to do is come up with automated tools that let us reproduce or beat results that have been attained recently just doing exhaustive experiments. So I'm showing videos here from one of my collaborators from University of Pennsylvania, where Aaron Johnson, he's a phenomenal robotics engineer, and he was able to, just through exhaustive kind of hand tuning the inputs that he applies to his Rex robot here, he's able to get it to do these pretty spectacular kind of leaping maneuvers. And then we can make models of these kinds of systems, but then the problem is that actually optimizing them, especially if we were using this kind of rigid modeling paradigm, they become this like mixed integer sort of nasty program that I understand under certain circumstances can be tractable and you can rely on this, but the interesting thing is that if we just remove this rigidity and we move towards these like soft compliant bodies, then it effectively makes the dynamics just significantly simpler. And so we're trying to apply, instead of like mixed integer kind of approaches, non-smooth optimization algorithms that scale a little better in the dimension of the problem and the inputs and things like that. Yeah, question?
And mathematically, by removing rigidity, do you mean that this requirement that velocity changes discontinuously with the point of impact, is that the thing that you remove? Is that the thing that you relax?
No, so we still allow the velocity to change discontinuously, but really here's the key observation. If I imagine myself as like potentially a rigid robot with 2 legs or one with kind of soft legs, here's what needs to happen. When my right foot strikes the ground, it's going to change its velocity very rapidly, and so my model for that is going to be this discontinuous change that like, okay, it was moving toward the ground and then it hits and then bam, it's a different velocity, either 0 or it bounces off or something like that. But what I'm going to preclude is I'm not going to allow that velocity change or that impact to instantaneously propagate and affect the velocity of my other limb that could be interacting with the world. So I'm not allowing these sort of instantaneous shocks to propagate all the way through my robot. And so the way that we kind of envision building robots now to fit within this modeling paradigm that we think has better properties is that you basically build your robot, you kind of reach into a bag of parts. So I pull out a leg, I pull out a body segment, maybe a couple of those, and I stitch them together. But when I stitch them together, I don't want to rigidly bolt them with and introduce these constraints between them. I want to put some kind of like shock mount or something like that, so that impacts in one leg that I've bolted together in this way don't all instantaneously or right away propagate all the way to the other side. Does that intuition make some sense?
It just seems to me that these removing this requirement of instantaneous velocity change and what you said, it seems to be equivalent in some sense, because you're adding something that absorbs the shock and prevent the velocity doesn't change instantaneously anymore. It kind of decreases this shock absorber. It helps the velocity decrease more gradually as opposed to completely instantaneously.
That's interesting. So, well, one observation is that we don't have to put the shock absorber at the foot, like at the interface between the limb and the world, the limb and the environment.
That's
Yeah, we
fine.
kind of put it in the other side. So that distal, that furthest away limb segment will still have this kind of like, or could still have this kind of impacting thing. But I will say that your intuition is right, that it has the effect of making it so that the body state evolution doesn't have any of these discontinuities. It isolates that from the body as well.
It doesn't matter how you isolate, whether you remove this requirement or you leave this requirement but add this shock absorber somewhere in there.
Right.
Right. Then you get rid of all these mixed integer constraints, which are like this model which limb is at contact at a particular instant.
Yeah. Yeah, and at that point, then we're really just optimizing over how the body evolves, and that evolves in a nice, not necessarily classically smooth, but anyway, smooth enough kind of way.
Yes.
Yep.
Anything which is not mixed integer is good.
Yeah, that was our big goal basically, because this was really the state of the art that was used in that DARPA Robotics challenge, was footfall planning and sequencing and things like that with this mixed integer thing, and then once you have your footfall plan, then you can do a regular kind of optimization on top of that. Cool, so those were the two halves that I wanted to discuss, how people might control, a theory of how people control a nonlinear dynamical system, and then how we might be able to make certain kinds of nonlinear dynamical systems more tractable, simpler, so that they'd be easier to interface with people. And so if we return to this original vision that I'm imagining of trying to build these like teleoperated robot firefighters, like I said, I don't want to completely trash the DRC results, so I want to go back to this picture and show really the success stories, what I think of as like the super impressive outputs from this program. So the robots, they move pretty slow, but once they're able to get to their tasks, they're able to do like some super impressive, in my opinion, maneuvers where it's like, this Atlas robot or these Hubo or these different devices, they've got like dozens of actuated degrees of freedom, and they weigh hundreds of pounds, right? But once they're able, they have the valve within reach, they've got the drill right there, they've got the doorknob, and they're in contact with it, they made it to the stairs. They're able to coordinate and optimize and synthesize behaviors for all of these degrees of freedom in real time, just using onboard sensors, no Vicon, anything like that. I think that's tremendously impressive. But I still think there's this big gap to this original vision, in particular with the idea of pushing toward dynamic, like real-time, I'm really busting down the door, pulling the cat out from under the bed, like kind of behavior. And so the kind of problems I'm particularly enthusiastic about are these sort of dynamic teleoperation problems in the regime of manipulation, but I'm particularly focusing on locomotion. That's my background in robot locomotion. And the parting thought that I want to leave you with in this world where we're sort of interacting with the physical world through automation and machines, the key thing that I want to focus on, I know there are a lot of cases like driving where ultimately the solution might be I just get into a little pod, there's no steering wheel, I just have a display, watch TV the whole time I'm there. I'm sort of totally separated from the process. So I'm not as interested personally in pursuing those kinds of problems. I'm really interested in the regime where it's the combination of the human with the automation that solves the problem or achieves the task. And so I try to think of situations where it's the humans that are really the enabling technology in the semi-autonomous interaction. So that's everything I wanted to talk about. Thank you so much for your attention. I'd be happy to take any questions. I should say any more questions. Yeah, please.
So, in the second part of the talk, you were talking about how you had Aaron, do these, just from his intuition building these things.
Right.
So it's like, I can build these things up, right?
Yeah.
And then I was talking to Francisco the other day, and he was we were talking about dynamic motion primitives and and then inverse reinforcement learning. We do that a little bit in the group, and we think about that. And at least in manipulation world, from following the literature in that it seems like, from demonstrations, we can come up with we can infer not only priors on dynamic motion models, but also try to do this shared teleoperation, right? Where you are online by looking at what the humans' inputs are coming. People are doing this even for brain-computer robot interfaces for paraplegics, as well as in just hard teleoperation problems, guess what the human is doing online in an inverse reinforcement learning kind of setting, and try to do the control on board to help this inferred goals, right? And I see there's this very rich interplay between controls theory and and learning that is also people are starting to do and think deeply about. Would love to know your thoughts on these. On where you see what the right paradigms are, especially with relation to this dynamics, predicting what the model is going to do, and then teleoperating so that in a safe manner, so that we don't do make the drone crash, right, or induce oscillations.
I have a number of thoughts because I'm deeply interested in exactly these kinds of problems. And those kinds of applications. And I know that there's a number of people working in this space and a lot of different kind of approaches. To me, a really important thing is to not just kind of blithely apply our favorite either control algorithm, control analysis or synthesis algorithm or learning algorithm or something like that. Because I just envision this future where I buy a new car and I get in it and I start driving and the car's learning about how I like to drive, and then after 10,000 miles of Sam driving, it says, oh, okay, I know how Sam likes to drive, now I'm going to help. And if that transition is abrupt, and if it's done in a way that doesn't predict how I'm going to respond to it, I think that I would just freak out and pull over and disable that feature in the car, basically. And so the approach that I tried to adopt, and I hope this is what other people will do as well, is work within some paradigm. It doesn't have to be exactly what the scientists had proposed before, but work within some established paradigm where we have a lot of support that okay, if I do this kind of intervention, then I have an a priori prediction of how I think the human will respond, and there's a fair amount of prior evidence to kind of build on. So I'm not just doing this as an engineer totally, ad hoc for the first time. So I know that, for instance, I'm aware of other work like Anka Dragan's work on using ideas from psychology about like legible motions and things like that. I think that's exactly kind of in line with this thinking that we already know a great deal about the way people interact, the way they like to interact, how they learn, what they do or don't learn, and so we should draw on that. The kind of flip side of that, if you're kind of working within a particular paradigm where the scientists have been studying, they don't necessarily have like constructive means to solve these problems because they've been thinking of them like, let's study the human as it is, and as engineers, I think our goal is to put the human into situations they've never been in before and make a functional system, right? We also have kind of different aims in that the scientists, they want to understand what the person's thinking, how they're doing that thinking and stuff like that. From the engineer's perspective, I think it suffices, and that's kind of my philosophy that I used in this talk, I think it suffices just to have be able to make accurate quantitative predictions, even as you alter some parameters or tweak some settings or things like that. It doesn't matter whether you really believe that I learn literally a differential equation x dot equals f of x somewhere in my brain and I could identify which neurons encode it. That's kind of irrelevant for the engineering task, I think, in some ways. But what the scientists, I think, can really offer are like the obstacles that we're going to need to overcome, because especially in tasks where the person's kind of operating in closed loop, there are a lot of known like cognitive or motor biases and like deficiencies and like patterns to the way we learn or the way we don't, like we fail to learn to correct for certain errors or tasks or things like that. So I think that's something that I really advocate and that I'm trying to do in my own work. And then there's kind of this higher level problem that I think there are some tools from like economic game theory that could be brought to bear, where just this fundamental problem of when a person is interacting with some dynamic, physical world, uncertain world, and they're doing that interaction with another agent, then there kind of automatically sets up this game where it's like it doesn't suffice just to have the machine be learning about me and then trying to respond to me, because as that's happening, I'm going to be learning about it and the way that it learns about me and responds to me. And that kind of naturally sets up this like regress where, well then, to be safe, the machine ought to be aware that I'm learning about it and it ought to try to learn about my learning, and it kind of automatically sets that up. And on the face of it, it might seem like, oh, well, that's like an intractable problem, we can never handle that. But the economists actually have some tools, some circumstances where that kind of regress can collapse. And so it's, again, to me, it's like, I think there are some tools that exist out there that we should be trying to bring to bear as we develop the engineering solutions.
Yeah, no, absolutely. Like this, I'm aware at least of recent work in inverse correlated equilibrium solving, where you, instead of trying to find the absolute equilibrium, you can still come up with suboptimal but stable policies,
right?
Multi-agent policies, where they're doing it again in in the pricing options and competitive markets thing, but these things can also have direct analogy, right? Like human and robots, right?
Yeah, I agree.
Together. They're not exactly in competition, but if they're aware of each other.
Yeah, exactly. Yeah, and that's an interesting thing that when the robot's trying to help me and I'm nominally and allowing the robot to help me, it's not that we are competitors. It's not that it's strictly a competitive game. But I think because of information asymmetry, I think there's a big difference between how I might cooperate with you to move furniture around my house and the way that I might cooperate with a robot to try to do the same thing, because we don't represent things in the same way, and we can't communicate as readily or as easily. We don't have kind of the same cultural baggage and things like that. And so it almost, because of the information asymmetry, it almost does become in practice competitive, or at least non-cooperative, or not obviously cooperative. So that's why I think also that theory is kind of relevant. Yeah, please.
I was wondering about this problem setting where you have the robot and the human. There's some kind of a network connecting them, right? And this network could have delay or latency.
Yeah.
And I think you mentioned this earlier in the talk, but this is something that you're currently not studying.
Correct.
Is that understanding correct? So I understood correctly.
Yeah.
Okay. So I'm wondering but it's something you've clearly thought about, right? And could you share some thoughts on how the amount of delay affects all the work? Like if you had to actually make all this work in the presence of network delay, does it become impossible? Like, or is there still some hope? Like, okay, let's assume that the network delays are small. It's not like we're trying to communicate with space
Satellites,
robots.
yeah, right.
Assume the network delays are small. You're still on Earth, but far away, thousands of miles away. Can you share some thoughts on?
Yeah, I think that's a very challenging problem. So I don't think that I said it explicitly, but one of my standing assumptions, or just to make my side of the problem a little easier, I was like, okay, let me imagine that I'm in an urban area and I have access to fiber optics. So I have unlimited bandwidth for all intents and purposes, which is a very different regime than what they tried to deal with in the DARPA Robotics Challenge, where they tried to introduce, I don't know if they messed with the delay so much, but they tried to introduce just bandwidth, just throttling. And intermittently just cut out the connection entirely. Yeah, that's right. But I don't think they carefully studied okay, if the person's teleoperating and we introduce delay of 20 milliseconds, what does that do? Things like that. Yeah, so I honestly I haven't thought carefully about how to accommodate that. I know that in the haptics literature, there's a pretty long tradition. Some people using kind of control theory techniques like passivity, and some people using other probably more comm-centric techniques. So I think that there's a lot to draw on to try to bridge that gap, but to be honest, I don't have good answers for that. One kind of interesting thing to throw out there is that in not in something like flight, where really millisecond delays, tens of milliseconds could be really crucial, but in something like the teleoperated or the robot-assisted surgery, they've done some of these experiments on how much delay will a surgeon tolerate, how much sensoromotor delay will the surgeon tolerate before they just get so frustrated and they find it impossible to learn, or do they even notice and things like that. And they'll actually tolerate a lot of delay. And so for some problems, some tasks, I think that you could, as long as you had reliable communication, so it's not that okay, it's gonna, it's like watching a YouTube video and it hangs for 10 seconds. But if it's okay, we know that this link is only reliable really to 100 millisecond delays or something, actually people can adapt to that. Now, my theory won't accommodate that. Right.
It's predictable, then humans can adapt to these sort of things.
Right.
But this is when you're talking about a low bandwidth Skype call or something. Yeah. So I think it's some kind of a parallel to that, I guess. There may be some limit of network latency that you can handle, but it should be predictable.
Yeah, surgeon is also an expert, right? Meaning in the sense surgeon is a highly trained, meaning he's not going to be doing the surgery the first time on a new haptic interface, meaning he's probably he or she has practiced for a while.
Right.
So they are it's like having an F1 driver adapt to a slight steering control delay. They probably can do it because, whereas if I'm driving a Tesla and suddenly you say there's a 20 millisecond steering input delay, I probably will crash immediately.
Right.
Right. So yeah.
My intuition actually tells me that for a given network delay, there is some limit to the dynamics of the system that you will not be able to control it with.
Yeah.
Or rather, actually, I guess sustain this. If given the system dynamics, beyond a certain delay, you will not be able to control it. If, for instance, the function that maps your inputs to the outputs is not if it's continuous, but there's nothing you can do. Obviously, in the physical world, maybe there aren't many such functions, but there are some that come pretty close. So I think that there should be a result that's provable.
Yeah.
Along those lines.
Yeah. I think your intuition is exactly right. I mean, certainly control theorists, just without humans in the loop, have been thinking about these kinds of issues for a while. And so there's, at least in linear systems theory, there's a pretty reasonable way to handle that delay and kind of incorporate the effect of it into your predictions of stability and things like that. And you can get these thresholds where, okay, after this controller will not stabilize that system, basically.
Yeah.
Yeah. So there's ways of thinking about it. But I will say it was neglected in the current setup. Yeah.
Speaking of it,
Is Garija here?
Sorry.
Is Garija here?
I was just going to say that, Garija sent me an email that she's at Allerton and she's sorry that she couldn't make it.
Oh yeah.
But if she had been here, she would have really.
Yeah.
But she will be back next week. So yeah,
Cool.
yeah. But I think somebody had a question.
Okay, super. Yeah, please.
So it sounds like you mentioned that more recently there have been a lot of great developments in this area, but there's still sort of a big gap. Given the current state, my question is, how far do you think we are from developing and then actually deploying teleoperated firefighters into the world? And second, what do you think is sort of like the infrastructure for getting there? So do you think like the biggest movers would be like more government funding, or it'll come from academic institutions, or more through the private sector, like through company research?
Those are great questions, and to be honest, I think it's kind of showing the fact that I'm an assistant professor and I haven't actually thought carefully about the actual translation to practice. So first question is about how long to deploy, and the second question is about who and how to deploy, essentially. I think that it's early days, and I'm kind of risk adverse, and so I'm kind of cautious. Obviously, CEOs of new car companies aren't as worried about it in terms of rolling out software updates and deploying these things out on the freeways.
Of some.
yeah, fair enough. But increasingly, and actually one of the things that I cited I forgot to mention was that there's a study by a nationwide insurance think tank kind of thing, and they basically did their actuarial analyses. I don't know the details of it, and they basically found that a certain car company, their enhanced safety feature was leading to more crashes than if it wasn't present. So it's like an optional feature. It's called an enhanced safety feature. It was the lane keeping assistance thing, and if your car had it, you were statistically in the actuarial kind of table, they should charge you more to insure that vehicle because it's less safe to drive. Now, this could have been a statistical fluctuation. I don't know. I'm not totally confident on those details, but I think that probably companies are eager and want to deploy these things. So I feel like the how and the when is probably them and sooner than I personally would feel totally comfortable with. Yeah, I think that my vision of the robot firefighter, I put that up there to kind of be provocative. But I think that 5-10 years. So once I get tenure, right, and then once I 5-10 years, I think that maybe they're not the only firefighters, but something that's out there running around, maybe doing the reconnaissance, maybe doing the front line sort of sampling, measurement, observation, and stuff like that, remotely piloted by some operator in a little, steel case or something like that on the sidelines. That seems possible. That seems tractable, and maybe that could be very valuable. The other kind of flip side, I'm not personally trying to go down this route, but you can already see this happening. There's already a couple of instances of law enforcement agencies using teleoperated robots to achieve certain goals, right? Either detonate a payload, or it's already been used in the bomb defusal thing for a long time, but now they're starting to take those same physical robots and just use them in these other ways, like either disarming somebody or neutralizing somebody or things like that. Yeah, so it's probably not, I think I can say definitively, it's not going to be the assistant professors of the world that are out there deploying them on the front lines. It's probably going to be the government actors, the corporate actors, things like that. Yeah. Please.
Just general question, you briefly touched a little bit on the developmental psychology side, basically you mentioned about having your forward model somewhere ingrained there. I was wondering if you could comment on what the current scientific consensus is about having these internal models. Because it seems to me that if people really have those models, people are completely unaware that they do have those models.
Right. It's not something that I can literally close my eyes and be like, oh yeah, F1 of X is
Yeah. So I'm personally in the reinforcement learning community, I'm a big fan of model-free RL. Mm-hmm. So I was wondering what's the plausibility of having these internal models and what the consensus is on the psychology community.
Yeah, that's a great question. So I have kind of two different comments I want to make. One is that just to directly start by addressing the last thing you mentioned, that there are totally parallel methods in model-free learning, something like that. I'm actually sort of agnostic as to how the person implements this forward inverse model picture. If if it works as a descriptive model across a range of circumstances, and we just have high confidence in it, and we can use it as engineers as like a design principle, I'm agnostic as to whether or how it might be encoded, or whether what's actually happening is learning, model-free learning, or whether, I mean, there's a bunch of actually, like, the predictions from this model are indistinguishable from a lot of different competing paradigms. And so, like, one on the motor control side, the internal model thing, I kind of presented it as like a popular paradigm. It is. There's actually a increasingly popular one and more modern one that's based on optimal feedback control theory that's kind of took the community, kind of gripped the community, and a lot of people are big fans of it. I've kind of placed this in a regime where predictions from optimal feedback control are indistinguishable experimentally from if the person learned and inverted a forward model. And basically because here I'm not requiring the person use a lot of effort to track or to execute the task. And so the effort penalty in the optimal control problem is pretty low relatively, I expect, or that's kind of, I've tried to conspire the circumstances so that that's true. And so then the primary penalty when they're executing the task is just task relevant. And so then at that point, what the optimal controller does is basically what the inverse model, you know, the inverting input would do.
Basically, the model you were introducing here would be like, it's more like you introduce like the whole concept of putting the person in the loop, and this model you introduce is like one alternative or like one option of how you would go about it.
Yeah.
Okay.
Yeah.
I see.
Yeah, but then when you start to kind of unravel it, you're like, well, would I have gotten a different prediction from optimal control? And it's like, probably not. And then would I have gotten a different prediction from if they're just doing reinforcement learning? And it's like, probably not.
Okay, so it's more like the idea you're putting out there is more like this whole like umbrella thing of like, let's keep the human and the robot as part of the same closed loop. How we do it, that's a different question.
Well, and I think maybe what I'm trying to say is a little bit stronger than that, which is that I relied on the forward inverse modeling paradigm basically to make the algebra easy so that I could get a closed form representation for what my prediction is for what the person does. But then looking at it afterward, it's like, well, I would have gotten, or under reasonable assumptions on how much effort it requires for the person to execute the task, I would get indistinguishable prediction from optimal feedback control, which I can't actually solve in closed form for the class of models I'm looking at, or reinforcement learning, which again I can't solve in closed form. But I know because I know based on principles of optimality and things that if I could solve them, I would get the same solution basically. So that's also kind of the push that I'm trying to make is like I'm not trying to put all my eggs in one particular theory's basket, trying to find where they all kind of intersect and they give sort of the same prediction so that there's robustness about how the person will actually behave. Because of course I know at the end of the day, they're not actually learning the model, they're not actually inverting, these are all just fictions we tell ourselves. But it's kind of the same, it's kind of a parallel philosophy in the looking at the dynamics of terrestrial locomotion that I know that the models I write down with these discontinuous updates and these contact modes, these are all just fictions I tell myself. In reality, there's just atoms and quantum mechanics, right? But if I build my robot and I restrict myself to the kinds of robots that, where this is like an easy or a nice approximation, then I can, I'm not so sensitive to how I initialize things or how they're built or things like that. Does that address the question?
You can use the math to co-engineer back the system.
Yeah, that's and that I would hope that the system, whether it's the person or the machine they're trying to control, that there's some kind of robustness, in this design space, basically.
Because you've gone back to design principles and really studied, the effect of this interaction, right. And not just design I'm going to design the robot, I'm going to design the interface, and let's hope it works.
Right.
Over what we have. Yeah. No, that's interesting.
Yes, sir.
All right, I guess.
Any other
there are no more
questions?
questions? We'll end.
Fantastic.
Yeah. Thank you.
Thanks so much.